So in this video, I wanted to do one additional example of computing an equivalent force coupled system in 3 dimensions. So we have a plate that's acted upon by 3 forces. The book has set up the coordinate system such that the origin is at the corner of the plate, and we're given enough geometrical information in order to be able to write expressions for position vectors from the origin to the various points of applications of these forces. And the reason that that's important is we're asked to find an equivalent force coupled system at the origin and also find the location of the single equivalent resultant force. So if you're still getting a hang of this material, when you read that problem description, it probably sounds really, really confusing. And what I would encourage you to do is to go and grab something that's kind of shaped like a plate, so it's kind of rectangular, and that way you can just hold it in front of you and see if you can understand what's going on. So imagine if you had like this textbook, which is way too thick. Hopefully you have an easier, something that's easier to manipulate available to you. And it's being pulled up with a 100 Newton force here, and it's being pushed down with 2 forces at its corners. If you think about, if you were to apply that force loading to this body, what would happen? Well, naturally, it's going to move in the downward direction. So kind of ignore gravity. Obviously, gravity's there, but we're just talking about the presence of these 3 forces. The net or resultant force in the downward direction is going to be 800 newtons. So these 3 forces, when you kind of model the effect on the motion of this body that they will have, they're going to tend to push the book down. However, in addition, remember we talked about actually visualizing the rotational tendencies that forces cause. And one of the things that we talked about is how you can compute the moment of a force about an axis. And the way that we did that is we grabbed the actual body on that axis of interest. So imagine you grab this body on the x-axis and you push it down on these 2 corners, the 500 Newton and the 400 Newton. Note that it's going to induce a rotation about that axis you're holding, which is the z-axis. In a similar fashion, if you grab it on the y-axis and you push it down about this 500 Newton force, or you push it up about the 100 Newton force, you'll notice that there's some rotation that this force system will induce about the y-axis as well. So what this problem is really doing is asking, can you come up with the amount of force that you would have to exert at the origin and the corresponding couple? And remember that couple is a free vector, so it can be moved anywhere along this body, that would have the same motion, same tendency to induce motion as these 3 forces that are acting upon the plate. And the reason that that's important from an engineering point of view is if we can identify the equivalent force coupled system at the origin, then if we were to want to keep this thing stationary and actually support it, build some type of support system at the origin, we could determine how much force and how much couple that support would have to provide in order to counterbalance the loading effect of the various forces acting upon the plate. So that's why that's important. The idea of the location xy of the single equivalent resultant forces, when you have those 3 forces acting upon a body, it's probably pretty reasonable for you to assume that I could find a point such that if I pushed 800 newtons in the downward direction, that single force would have the same rotational tendency as all 3 of these discrete forces. And particularly what we're just going to do is we're going to, once we find, we know naturally that the resultant or force is 800 newtons. So we're just going to pick and put 800 newtons at a point such that 800 newtons induces the same rotational tendencies about the y-axis and the same about the x-axis. So that's kind of what we're doing and the kind of motivation behind why we're doing it. So I'm going to go, and of course, this always happens when I go to record a video. For full disclosure, I've actually had to redo this one 3 times. The first time someone knocked, and the second time my brain just froze. So don't think that doesn't happen to everyone. So here I've just kind of recreated the geometry that I was given in the textbook. I want to find the equivalent force coupled system at the origin. Remember that the first step in order to do this is to find the force. A force couple system consists of 2 components, a force and a couple. And that force is the resultant force. It's just the sum of all the forces acting on the body. So the resultant force is going to be nothing more than the sum of the 3 forces, in this case, that are acting on this body. And I can write little expressions for them if I want. This force is going to have no x component, no y component, minus 500 z component. This will have no x, no y, minus 400 z. And this will have no x, no y, 100z. And you can write it as, in terms of the I hat, j hat, k hat basis vectors if you want. That'll just be 100 k hat. This will be minus 400 k hat. And this will be minus 500 k hat. And these are all in units of newtons. So if I add those up, I'm going to have plus 100 minus 500 minus 400 k hat, which is just going to be minus 800 k hat in newtons, or alternatively, if you want to write it like this, that works as well. Now, if you notice, that had no consideration of the point at which you were determining the equivalent force couple system. And what that says is if you're going to come up with an equivalent force couple loading for these three forces, it doesn't matter where the force is placed, the resultant force is the same. And what that means is that the tendency to induce downward translational motion is the same in each case. Where we're actually going to incorporate the fact that we're finding the equivalent force couple system at the origin is when we compute the actual couple here. So that's step 2. And remember that all the couple is doing is saying, if you move this force to the origin, you have to account for how much rotation the force did induce before it was moved. So that means that you just have to compute the moment of that force about the origin. So the equivalent couple of this loading system is just going to be the sum of all the moments of the three forces about the point to which they're being moved, which is the origin. So let's actually do it here. So let's start with the 100 Newton force. Remember, when you compute the moment of a force about a point, you have to draw a position vector from that point to any point along the line of action of the force. The easiest one to do here is a point of application. So it's going to be a position vector from the origin to this point of application of the 100 Newton force. Notice you're moving in the positive x direction. It's a 3-meter displacement. So the position vector will just be 3 I hat. And we're going to take a cross product with the actual expression for that force, which is going to be 100 k hat. And you can track your units if you want. This is, of course, going to be in meters, and this is going to be in newtons, so the result will be in Newton meters. And we'll show them all added together first. Let's do this 400 Newton force next. So what would the position vector be? It needs to go from the origin to the point of application of that force. Notice that in order to go from the origin to this point of application, there's no x displacement, there's no y displacement, there's no z displacement rather, it's just in the y direction. So in the y direction, the name of the unit vector is j hat, so that will be 4j hat for my position vector, crossed with minus 400, and then that vector, of course, is in the k hat direction, as are all the forces in this case. Sorry, I was moving, my drawer broke and I had to move it away from my dot cam there. So that's for the 400 Newton force. Why did I choose to do the 500 Newton force last? Well, it's going to be a little more complicated because note that its position vector needs both an x and a y component. So the x component is just going to be the depth of this plate, which is 4 meters. So it's going to be 4 I hat. And the y component is just going to be the width of the plate, which is also 4. So 4 j hat. And I'm going to be taking a cross product of that with the expression for this force in rectangular form, which is just minus 500 k hat. And again, all these are in Newton meters, so I don't have to worry too much about it. So I'm going to call this computation 1. I'll call this computation 2, computation 3. And when you're doing these little, these kind of simplistic cross products, you could make your 3x3 matrix and do the determinant. However, it's easier to remember that actual drawing that I had shown, and it's in your text as well, on one of the earlier slides that allows you to quickly compute the cross product of basis vectors. So what this does is if you move in the direction of the arrows, the resulting cross product is positive. So I hat cross j hat is k hat. You know that because you can go to your original coordinate system and put your fingers on the x-axis, cross to the y, and notice that it's pointing in positive z. So j hat cross k hat is I hat. As long as you're moving along this circle in the counterclockwise direction, the cross product is the next unit vector you get to, and it's a positive sign. So this is what we're going to use in order to do this. So let's make computation 1. 3 I hat cross 100 k hat is just going to be 3 times 100 I hat cross k hat. And that's just going to be 300. And you can put the units in here if you want, Newton meters. And what is I hat cross k hat? Well, I hat cross k hat, I'm going opposite the direction of the arrows. So that's going to be minus j hat. So actually the way you would write this is minus 300 j hat Newton meters. Now let's actually see if we can see what that is saying. The minus means that it would tend to induce clockwise rotation about the y-axis. In particular, we're talking about the 100 Newton force. So go back and take that object that you have and imagine you're pulling it up at this point, and imagine you're looking down the y-axis. If you're looking down at it, which way does it look like it's rotating at you? It looks like it's rotating in the clockwise direction. And remember that by convention, the clockwise direction of rotation is denoted with a negative sign. So that's why that turned out the way it did. Now let's do part 2. This is for the 400 Newton force. So it's going to be 4j hat cross minus 400 k hat. A way you can get in trouble here is like when you got this negative sign, just mixing them together. So I usually just put it with my actual magnitude computation, and then I make this computation. So this is going to be 4 times minus 400 j hat cross k hat. what is j hat cross k hat? Well, that's positive I hat. So this is going to be minus 1600 I hat. So what that means is that this force should be about the, when you consider the rotation about the origin, it should, I hat is which axis? That is the x-axis. And what that's saying is it's inducing, remember that minus is a clockwise rotation about the x-axis if you were looking down the x-axis. So I'm going to kind of hold up my paper here and imagine this is the plate. So that 400 Newton force, when it goes down, if you're actually looking down the x-axis, so let me go to this, maybe this will be easier, but look at it from my perspective. Say I'm looking down the x-axis here, and this is the 400 Newton force. Notice that that rotation is in the clockwise direction. So that's why that sign turned out to be negative in that case. So let's do the last one. So 3 is just going to be 4 I hat cross, or sorry, there's 2 components to this possession vector. 4 I hat plus 4 j hat cross minus 500 k hat. So cross products are linear. That means you can do both of these individually. 400 I hat cross minus 500 k hat plus 4 j hat cross minus 500 k hat. So I kind of just did a distribution, right? Cross these two and then cross these two. And just be careful here. 4 times minus 500 is minus 2000. I hat cross k hat plus 4 times minus 500 is minus 2000. J hat cross k hat. And let's check what these would be. So I hat cross k hat is going to be minus j hat. So the minus, and I'll actually show the step here just so no one gets confused. That's minus j hat. And then for j hat cross k hat, you're going in the positive direction, so that will just be I hat. So what's this going to be? Well, it's going to be 2000 j hat, and then there's only one minus here, so I'll just write minus 200, minus 2000 rather, I hat. So all I need to do is sum all these together now. So to get the moment of the couple, or I should say, yeah, I guess it's moment, just the couple is usually the way it's said. To get the couple of this equivalent force couple system, I have to add all those moments about the origin. So if I go back to what I had, I'm going to have to add minus 300 j hat, and then I'm going to kind of just keep them straight. That was from this. From the I hat, I had minus 1600 I hat. And then from this computation, I have another 2000 j hat. And from this computation, I have another minus 2000 I hat. So if I add those together, what am I going to get? Well, minus 300 plus 2000 is just 1700 j hat. And then minus 1600 minus another 2000 is minus 3600 I hat. Now, by convention, you usually you write vectors ordered with the I hat component first, then the j hat component. So really how you would write this is like this. It's going to be minus 3600 I hat plus 1700 j hat, and that is going to be Newton meters, or you can write it equivalently, minus 3600, 1700, 0 Newton meters. And if you look at that force couple system, hopefully you can convince yourself that you're getting that nature of the rotation. So let's talk about the equivalent force location now. And what I'm going to do is I'm going to redraw the actual plate. So this is the x direction, this is the y direction, this is the z direction, and I'm going to draw in my plate in red like I did last time. So what I'm going to do is basically find where I'm going to apply this equivalent force. So say like I thought I would apply it there. I'm going to draw it really big. And remember that the equivalent force, resultant force, has a magnitude of 800 newtons. So it's 800 newtons down. And that's going to have some separation from the, sorry, that should say y. I think I said y and then I wrote x. That happens a lot. So this is the distance from, along the y-axis, from the x-axis that you would apply the force. And this is the distance x, which is, and you can put, usually they'll put like a bar here or something. This is just saying go out y units in the y direction, go out x units in the x direction, and that's where you would apply the force in order to induce the same rotation. Well, let's actually look what this is. Let's talk about the moment that this resultant force would have about the x-axis. So if you notice about the x-axis, that moment is going to be 800 newtons. That's the magnitude of the force, times whatever this distance is. That's what we're trying to calculate. And if you think about the nature of the rotation that you're going to get, if you're looking down the positive x-axis, it's going to be actually negative. So that's why this sign, it turns out to be negative. So you can put the double negative in here but it's basically just going to cancel out. And what you're finding is that in order to determine this distance, you're going to need it to be 3,600 divided by 800. And just make sure the units work. Remember, this 3,600 is Newton meters. So when you divide by something in newtons, this will just be in meters. So that is just 36 divided by 8, whatever that turns out to be. And then in a similar fashion, to find out how far you should separate it from the y-axis, you'll want to compute the moment about the y-axis. And what will that be? Well, it's just going to be 800 newtons times this x bar value. But note that in terms of the y-axis, you're actually getting, here, go back to the book, counterclockwise rotation. So that's why that actually turns out to be positive. So you want to equate this to just 1700. And what you will find is that x bar is just going to be 1700. And remember, this is in Newton meters, divided by 800. So that's just like 17 divided by 8, whatever that turns out to be. So I know you all can use a calculator at this point. If not, we got bigger problems than calculus or statics or whatever particular aspect you're struggling here with. So hopefully that was a helpful example for you for how to compute the equivalent force couple system of a general loading about a point, and how you ideally, in the coplanar case, can find the location that the resultant force should be applied in order to induce whatever that couple that you computed is.